Yeah, I think I'm ready.
Okay, so welcome everyone to the algebra geometry seminar. So today we are happy to have Lai Guanwen from Academia Sinica. We will talk about bijective Cremona transformation on P2. Please.
Thank you very much for the introduction. So today I'm going to talk about my old work about bijective Cremona transformation of the plane, and this is a joint paper with Shamil Asghari, Masahiro Nakahara, and Susanna Zimmerman. And I've gave this talk somewhere before, and maybe it's possible some of you have already heard about it. But I think previously this whole project is not completely done yet. And today I'm going to give you the complete picture if you heard about this before. Okay, so let's start with something very elementary. So if you search, like on Wikipedia, if you search for the Fano plane, then you'll see this picture. So Fano plane, you can think about it as a projective. This is a projective space, projective plane defined over F2, where F2 is the field of two elements, which consists of 0 and 1. And the point in the Fano plane, which are defined over F2, are the points whose coordinate points x, y, z, where x, y, and z are all 0 or 1. Each of them is 0 or 1. So so under this setup, there are totally 7 points in the Fano plane defined over F2. And I've already drawn all of them on this blackboard. So for example, we have 1, 0, 0, 0, 1, 0, 0, 0, 1, 1, 1, 1, and the other 3 points. And these are the straight lines in the Fano plane. Okay, we have these straight lines and also this one. This is also a line in the Fano plane. Okay, so now let's focus on the points in the Fano plane, which are defined over F2. So in general, given an algebraic variety like P2, like this, you can talk about its points defined over, in this case, the ground field, which is F2. You can also think about points defined over some field extension. But here, let's focus on only the rational points defined over our ground field, F2. Okay, these are the points whose coordinates are defined over F2, and I've already told you, put all of them on this picture. There are 7 of them. So in this case, this set is a finite set. And given any finite set, you can talk about permutations. Yes, you can talk about permutations. For example, there could be a permutation. Think about the permutation which fix this point, send this point to itself, and send this. I also label all these points by numbers, okay, which is fix 1 and send 2 to 7 and send 7 back to 2 and send 3 to 6 and 6 to 3 and send 4 to 5 and 5 to 4. And you can record this permutation using this symbol. I think you should be very familiar with this symbol if you've taken a like group theory or basic algebra course. Okay, sorry. Okay, I hope you can see it. Yeah, so given the 7 point, this is finite set, we can consider permutations on this finite set. And in particular, there's such kind of permutation. And here, given such a permutation, my question is, can we write this permutation down in terms of polynomials? So given P2, this is a projective space. On P2, we can consider polynomials on P2. Like, for example, on P2, we can consider a map defined by polynomials like this one, which maps x, y, z to like yz, xz, and xy. So this is an example of a polynomial map going from P2 to P2. And it maps some points on P2 to points on P2. And somewhere it could be possible that it's undefined. So for example, 1, 0, 0, if you plug it into this equation, you get 0, 0, 0. And which is not considered as a point in P2. So this point is not defined under this map. But for example, if you consider 1, 1, 0, this is mapped to 0 and 0 and 1. Okay, so this map 1, 1, 0 to 0, 0, 1, it's defined. So here my question is, given such a permutation, can we realize this permutation or can we write it down using a polynomial map like that? Okay, can we write it down? Using polynomials. Like this one is definitely not an example because it's not even defined at this point. Okay, so we have this question. Okay, so now I'm going to generalize this picture and give you the general definition about the thing I'm going to talk about. So here's the definition. Let me start with the definition. So given X an algebraic variety defined over a field, okay? So for example, P2 is an algebraic variety, and you can think in that case, K is a finite field of 2 elements, okay? An example. And let's consider F, which is a birational automorphism of X. And so for example, this is a birational automorphism from P2 to P2, defined over, like in this example, which is defined over F2, which means that this equation, this formula, the polynomials, the coefficients of polynomials are all defined over F2. Okay, so given the algebraic variety, given the map, I define this map to be bijective. I say it's bijective if it induces a bijection on the set of rational points over K. Rational points over K. There's no restriction. You can talk about this thing to be like, you can talk about it quite generally. Yes. So yeah, on a set of K rational points over K, and usually this set is abbreviated as X parenthesis K. Okay, so this is in my definition. So under this definition and looking at this question, my question is whether I can find such kind of bijective automorphism like in this setting. Okay, so we have a definition, and given that general definition, I want to give you some examples. So for example, some easy examples. For example, if K is algebraically closed, then, okay, I forgot to define one thing. So in this group of birational automorphisms, these bijective elements they form a subgroup. And maybe let me write it down here. Let me put x, k here. This is just notation for the set of all rational points over k. And if you collect all the bijective birational automorphism on a variety, they form a subgroup in that group, which will be denoted this way. This B here means bijective. F is bijective. Okay, so this is just a notation. So for example, if K is algebraically closed, then this subgroup is simply the group of automorphisms. Or if you thinking about algebraic varieties in general is too hard, you are not familiar with algebraic variety, maybe you can think about projective space. Okay, or P2. This is just all linear transformations of P2. PGL2 over K. Yeah, like in that example, a general birational automorphism may have some indeterminacy locus. These are locus where the map is not defined. And this indeterminacy locus is defined by some equations. It's a locus of, it's a solution set of some polynomials. And over the algebraic closure, a set of system of equations always has a solution. So if you are working over the algebraic closure, indeterminacy locus always contains some point, which means that this map cannot be like, if your map has some non-trivial indeterminacy locus, it cannot be defined at some rational point. So this kind of thing is not allowed in this bijective group. So
you want to assume X is smooth?
Yeah, maybe I want to assume that X is smooth. So if it's singular, then I'm not sure.
Yes, because if you take a curve, P1 with a cusp, then it's possible that you have a bijection between,
Yes.
Yeah.
If you have a cusp with a curve,
then you can translate and.
Yes, you have this kind of translation. Yes, yes, yes. Thank you. Yeah, maybe let me just do this.
But or assume X to be smooth, I think should be okay.
Yeah, should be okay. Yes. So this is the first set of examples. And another example is when K is the field of real numbers, there are already some works about this kind of bijective thing. So for example, K is the field of real numbers. We can think about this quadric defined by x squared plus y squared plus z squared equals t squared inside the projective 3 space. Okay. So given this quadric, if you consider all the real solutions to this quadric, it's given by x squared plus y squared plus z squared equal to 1. And this equation should be very familiar with anyone who have done calculus or multivariable calculus. So this is a sphere. It's a sphere living within an affine chart of P3, which is R3. So in particular, this set is a real manifold. And once you are given a real manifold like this, you can talk about diffeomorphisms. So about this thing, it's proved by, so there are already some works about this. So for example, a mathematician called Collar and Mangold at 09, they proved that the group of bijective birational automorphism over R of Q. Okay, so each element in this group induce a diffeomorphism on this S2, and they prove that this inclusion as a subgroup in the diffeomorphism group of S2, this is dense. Okay, so for example, we have some result like this. Yeah, and there are many other results given by, so for example, Blanc, Huisman, and Susanna Zimmerman. Okay, if you know these names. Okay, so this is about things over R, but in this talk, my focus will be over finite field, like F2. So in the following, I will consider mainly P2 over the finite field of Q elements. Okay, and in the following, I will denote, because this finite field, this notation is a little bit complicated, I'll abbreviate this as K, and here Q is a prime of power of prime. Okay, in the following, I will focus on P2 over some finite field. Okay, in this case, each bijective, so if you consider P2, and then put P2 here. If you consider all the rational points on P2, this is a finite set. So as I mentioned before, you can discuss permutations on this finite set. And each element in this group it induces a bijection or a permutation on this finite set. So we have a group homomorphism. Let me denote it as sigma, which maps a bijective automorphism on P2, bijective birational automorphism on P2 to the permutation it induced on the K rational point. Okay, so we have this group homomorphism. And the question about whether we can realize certain permutation in terms of using polynomials, you can reformulate it as what's the image of sigma? What is the image of sigma? Okay, so before I give you the answer, maybe let me give you an example. So in the following, I'm going to give you an example of a bijective Cremona which realized this permutation. So my question is actually, yes, you can realize it in terms of polynomials, and you can write it down very explicitly. So let me do it on this board. Okay. Okay. I just erased what I want to use. So let's still consider, let's start with this example. Okay, let's start with this example. So as I mentioned before, this example is not an example of bijective birational automorphism because it's not defined, for example, at 1, 0, 0. So let me call this map F. Okay, so if you consider the base locus of F, which is the locus in P2 where the map is undefined, there are 3 points. 1, 0, 0, 0, 1, 0, and 0, 0, 1. So these points are mapped to nowhere. So you cannot use it to define a permutation on these 7 points. But I can modify this example to produce an example which I want. So how do I do that? I can twist these 3 points a little bit. I can, more technically, I want to twist these 3 points a little bit so that they form a Galois orbit of order 3 over the ground field F2. So more precisely, let's consider F8, the finite field with 8 elements. This is a degree 3 extension of the field of 2 elements, and you can write it as F2 adjoined with an element A, where A is defined in this way. A squared plus A plus 1 is equal to 0. Now you consider this matrix G, given by 1, A squared, 1, A squared, A to a fourth, 1, A to a fourth, A to A's power. So the column of this matrix consists of the, consists of 3 points which form Galois orbit over F2. Again, each of them is defined over F8. Sorry. A to the which A squared plus oh, I think I have a typo in my note, so I also have a typo here, but it should be something like this, at least something degree 3. Yeah, thank you. Yes, so if you compose this map with F, okay. So by doing this, you are moving the 3 indeterminacy locus, indeterminacy points, to the points with these coordinates. And these 3 points, they form a Galois orbit over F2, and each of them is not defined over the ground field, but the whole thing is defined over the ground field. So this whole thing will be defined over ground field. And if you work everything out explicitly using the expression, maybe by hand or by a computer, you can compute that this map has this formula. Right, plus xc. Okay, so this is the formula for this map. It maps, by using the symbol, I mean it maps x, y, z to this one, and to a point with these coordinates. So for example, if you plug in x, y, z equals 1, 0, 0. So like y is equal to 0, z is equal to 0. So for example, this goes to 0, this goes to 0, this goes to 1. I guess I have another typo. Yes, this looks better. Yeah, it should be homogeneous, meaning that all the terms should have the same degree. In this case, it should be of degree 2. Yeah, again, I have another typo, and sorry about that. So yeah, but if you plug in 1, 0, 0 into the expression, you'll get 1, 0, 0, which means at this point is defined, the map is defined at this point, and it maps this point to itself. Let's do one more. So like if you plug in 0, 1, 0, so x is equal to 0, z is equal to 0, and y is equal to 1. So you get the 1 here, you get 0 here, and you get a 1 here. So 1, 0, 1, 1, 0, 1. So I think I've made something wrong. 0, 1, 0. Can I check my previous note? Yes, because I gave the same example before in somewhere, and there's a square. Yes, and everything looks the same. And no one point out any arrow during that talk. So let me double check. For example, let me do 001. And if I plug in 001, I'll get 1, 1, 0. So 1, 1, 0. At least this part is correct. And maybe I did some, or if you plug in 1, 1, 0, you should get 4, which is 0, over in characteristic 2, 0, 1, 0. Okay, I think it should be correct. I think it should be correct. Yes. Yeah. So if you plug in everything correctly and don't get too nervous, you should get everything correct. And this should give you an example of a bijective Cremona transformation of P2, which performed this permutation on this 7 point. A very explicit example. Yeah. Okay. So we have an example. So, but how about this question? And how about this question? So now I'm going to give you the answer. So most part of the answer to that question was answered by a mathematician called Kanta. In 09. He said that if Q is odd or Q is equal to 2, then the image of the group of Morrison should cover everything. And for all the other cases, if Q is 2 to some power, where the power is non-trivial, so that Q is greater or equal to 4, then the image contains the alternating subgroup. Contains the alternating subgroup. And our result, we show that. So how about the other inclusion? Should the inclusion be equal to? There should be an equality, or actually the image should cover everything. That's still a question after Kangta's work. So we show that when in a second case, Q is 2 to the n greater or equal to 4, then we have the other inclusion. Okay. Yeah. So here the alternating subgroup means the permutations on rational point which are even, and our result tells you that you can only realize even permutations using bijective birational automorphism. You cannot realize odd permutations. Yeah. So for example, this is an odd permutation. This is an example of odd permutation, and you cannot realize. Okay, yeah, this is an odd permutation. Yeah. So in particular, this is an equality. This together tells you that this is an equality. Okay, so this is the result. And now I'm going to give you 2 remarks. Yes. So our first remark, How does Kantha prove this result? I'm going to give you a very rough idea. Kantha's result is actually based on another bigger result, very big result. Okay, so Kantha's paper is very short because all what he need to do to prove this result is to produce a single example. Yes, it's actually, I would say not say super hard. So this result is based on this result. So first you consider the symmetric group of Pn over any finite field, Fq. And in this group of permutations on rational point, you can consider a subgroup called collineations, P gamma L, n plus 1, Fq. This is the subgroup of collineations, which means that these are the permutations which map points which are collinear. If you have points which are collinear, lying on the same line, then their image will also lie on the same line. Okay, and the elements here usually are called collineations. Yes, so this is the group of collineations, and more explicitly, this group is generated by, to give you some idea. So this is simply generated by all linear transformations, PGL, and the Frobenius action. Okay, this Frobenius action, it maps, for example, x, y, z to x to p's power, y to p's power, z to p's power, where p is the prime under the Q. Yeah, so we have this subgroup, and there's a big result proved correlatedly or independently by many, many people. For example, two of these people are this one and this one. Yeah, and many others. They prove that if you have a subgroup of the symmetric group, okay, and suppose that G contains PGL. Contains PGL. Yeah, let me just write PGL for short. Then either G is totally contained in a group of collineations, P gamma L, or G contains the alternating subgroup. Okay. If you have a group of permutations on rational points, if you already know that it contains PGL, then it's either a subgroup of collineations, yeah, either it consists of collineations or it contains all the even permutations. So this is a big result, and it's totally group theoretic. There's no deep algebraic geometry in this theory. Okay, so with this result, and say you want to show this, the only thing you need to do is to produce one example, which is not a collineation. So yeah, so the bijective, the B-Berg, the bijective birational automorphism, it contains PGL. And if you can produce an example in this group, which is not a collineation, then it must, this will show that this is the case. And if this example produces an odd permutation, then you can recover everything. Yeah, so in this case, Kantha produced an example, which in this case do these two jobs. It's not collineation, and it induces an even odd permutation. But in this case, it's not collineation, but it's an even permutation. So you can only conclude this. And what we did is to prove the other inequality, but this is a totally algebraic geometry group proof, and it's actually very hard. So in the following, I am going to, the main part of this talk will be about how we attain this inclusion. How do we prove that the image is totally contained in the alternating subgroup? But before that, I still have something to say. So this is the first remark. There's another remark.
So can I ask a question? So is the group P gamma L the automorphism group of Pn defined on FQ? Or
Is P gamma L the automorphism group?
yeah, or it's a
I think it's simply, because Frobenius map is not,
yes, so
it's not
not the automorphism.
algebraic automorphism. So the automorphism is just PGL.
Okay, thank you. And so Conta only produce examples for P2, not for higher Pn.
Yes, he produced examples explicit for P2, and in a remark, he claimed that this example works in any dimension. But I think that example in higher dimension will have some indeterminacy locus which contains rational points, so it's not bijective. Yeah, I've written this down in a personal note. If you have any, if you are interested, I can tell you more. Yeah, but he claimed this in a remark. He didn't really give a very rigorous proof, and I think, and I found that this example in higher dimension doesn't really work. Yes. Yeah. So first remark, second remark. So this result has a generalization. So this is given by 3 people very recently. Geneva, and I don't know how to produce her name. Do you know? Okay. And Ulrich, 23. Yeah, they proved that in this case, if Q is 2 to some power greater or equal to 4, then if you consider any rational surface, then you have the same, you have the same result, which means that image is totally contained in the alternating subgroup. Yeah, K is F. Let me just write it down. FQ. Okay. Over on a rational surface over FQ with Q greater 2 to some power greater or equal to 4. By using bijective birational automorphisms, you can only recover even permutations. Yeah, and the main input, so I will talk, if time allowed, I will tell you more details, but the main input is another recent result by these 2 people, by Lemmy and Schneider. These 2 guys, they proved that this BIRK, where K is any perfect field of P2, the so-called Cremona group, the plane Cremona group, they show that this is generated by involutions. Yeah, so with this result, it's not hard to extend the machinery in our result or use their language to show that for any rational surfaces, you can only realize even permutations using birational automorphisms. Yeah, And if time allows, I will tell you more about this later. Okay. And yeah, so in view of this result, so for operational services, you can only realize even permutations over this kind of finite field. Then a natural question to ask is, how about irrational service? If you have an irrational service, do we have the same result or do we have a counterexample? So we have a counterexample. And here's a counterexample. If we don't assume the surface to be irrational. Okay, so to produce this counterexample, we need to start with an elliptic curve. So let's start with an elliptic curve E defined by this Weierstrass equation y squared plus xy, which equals x cubed plus 1. And I want to consider this elliptic curve to be defined over F4. And in order to write points down very explicit on this elliptic curve, let me write F4 as F2 with c, where c satisfies c squared plus c plus 1 equals 0. Okay, and then on this elliptic curve, you can compute very explicit that over F4, there are 8 points. The point at infinity, 0, 1, 1, 0, and 1, 1. And these are 4 of 8 points, and these 4 points are defined over F2. And there are 4 others, C0, C bar, 0, C bar, and C bar. There are 8 points. Yeah, and here this bar means the other root of this polynomial, which is c plus 1. Okay, and on this elliptic curve, there is an automorphism which permute this 8 point in an odd way, which produce odd permutation. So more precisely, you can compute the automorphism group of this elliptic curve. This guy is actually just the group with 2 elements, and it's generated by G, which maps xy to x, y plus x. Okay, and if you plug in these points, so for example, infinity will still be infinity, it's fixed. 0, 1 is mapped to 0, 1 is to 0, 1, so it's still fixed. 1, 0 is mapped to 1, 1, and 1, 1 is mapped back. And you can do the same thing for all the others with slightly more complicated computation. And you will see that it permutes these 2 points, and it permutes these 2 points. So in particular, this G, its action on the set of F4 points. It consists of 3 transpositions. So in particular, this is an odd permutation. Okay, so we have a curve together with an automorphism which permute the rational points in an odd way. So from here, it's not hard to produce a surface with an automorphism, which produce odd permutation on a set of rational points. You can simply take X to be the projective line P1 times E, where E is the elliptic curve, and you can consider G tilde, which is the identity, which act as identity on P1 and act as the G on the elliptic curve. Okay, and on P1, there are 5 F4 points. There are 5 F4 points. So this action on a set of rational points it has this many transpositions, 3 times 5, which is 15. So this is odd. Yeah. And this guy is irrational because mainly because you have an elliptic curve. Okay, so this is an example of an irrational surface together with an automorphism, which induce auto permutation over F4. So this is a color example to like if you don't assume the surface to be rational. Okay, so this is the second remark. Yeah.
So would you also
Any question?
follow from the description of automorphism group of elliptic curve that already automorphism on elliptic curve cannot produce all the permutation of 8 rational points. So because automorphism on elliptic curve, we know that it's a semi-direct product of translation with the automorphism of E as a group. And it seems that this group is.
You mean, can you use this group structure to give a proof?
Yeah, because symmetric group of 8 elements is, I think, quite complicated and
yes,
it's not so. I'm not sure whether it's solvable. And
yeah, I can see your question.
Yeah.
So how do you prove it without producing explicit example using simply the group structure? I have no idea, but it's worth to try. Yeah, but definitely the proof will be more complicated, I guess. Yeah, I don't have an immediate answer. Do you?
I don't know.
Yeah, I don't know. I don't know. Yeah. But that's a good question. Yes. So yeah, so is there any questions so far? So this is a 90 minutes talk. So I think it's time to take a very short break. Could we?
You can decide.
Okay, can we take like a 5 minutes break? Okay, yeah. And if you have any questions, so you are welcome.
For the Polar control result, if you replace P3 by also Pn or P2, so do we also have the density of the.
So what they prove is for S2 and also for P2 and also another, I think it's torus. They prove 3 examples have the same property.
For P2 is related to the various charts of population. Something that you can
For which one?
So P2 becomes so the real quadrant becomes the S1.
The real quadrant. Yes.
So the argument goes on the various charts of population that polynomials are then like
I didn't check, but I believe that this should be the idea. Tell me how to close it.
Another maybe not related question. So yeah, we can produce a sphere as a real local in the quadrant, real quadrant in the projected space. So is it possible to produce the exhaustive sphere? Yeah, so as a real local in the fund, I don't know the projected space. I don't know. And also for elliptic curve problem, I think automobilism group of elliptic curve, that elliptic curve is solvable because it's the extension of two obedient. So maybe because if you have a suggestion from a solvable solution, the problem is also solvable. So you want I simply want to pursue one control. I don't know how. Maybe guy has yeah. Another guy.上的那个场外面看得到吗？
喂喂，OK。 Okay, so let me start. So in the following, I'm going to give you some because the proof is quite long. It's almost 50 pages of paper. So I'm going to give you some highlight of some essential part in our approach. So how do we prove that over F4 or higher extension, you can only realize even permutation? So how do we do that? So the basic idea is super simple. So given a bijective birational automorphism, you can decompose it into some easier maps. You can decompose it into something easier like projective transformation, quadratic transformation, the one I gave you in the very beginning, and some other things. And then you can show that if you can show that all of these easier maps induce even permutation, then your map always produce original map always produce an even permutation. And the problem is, how do you prove that each of these simple maps are even? So what you can do is try to conjugate your map to something even easier, and then prove things there. But there's one thing you need to solve. First, you still need to prove that after conjugation, the permutation there is even. Another thing is you need to show that under conjugation, the two permutations are still have the same parity. So these are the two parts. Okay, so the whole strategy of proof consists of three parts. The first is decomposition. Given map, decompose it into something easier. Second, under conjugation by birational maps, the parities is still the same, which we call the birational permutational parity. And the last part is about how do we prove case by case that in some known or easier cases, the induced permutation are even. So there will be three parts. And I'm going to start from the last part. How do we prove some easier birational maps induce even permutations? Yes. So let me start from, this is the third. On my note, this is the third part. Okay. There will be 2 and 1. Okay, so first of all, let's think about the most easy thing, PGL. And for PGL, we can talk about things, talk about it slightly more generally. So we can talk about PGL in any dimension. And here my K, so in the following, my ground field K will always be F2 to some non-trivial power, which is greater or equal to 4. Okay, so for PGL, there's a result over finite field given by Waterhouse, proved in 89. Okay, he said that PGL, or you can also simply take GL over any finite field FQ. Here, this finite field is any. The general linear group is always generated by two elements. And these elements can be written down in a very explicit way. So for example, when n is equal to 2, n is equal to 2, first you consider the multiplicative subgroup of the finite group FQ. It's always cyclic, so you can take a generator, alpha. And in this case, we can take, for example, AN to be this linear transformation. And take Bn to be this linear transformation. And these two guys will produce GL3 over FQ. Yeah, so with this result, you can easily prove this proposition. Okay. Over that ground field, the permutation induced by PGL n plus 1 K on the K rational point of any projective space, this action is always even. Yeah, for any n greater or equal to 1. It's starting from P1 and P2, P3, and so on and so forth. So the projective transformation always produces even permutation over that field. And over the other finite field, it's easy to construct counterexample. Okay, so we have this proposition, and with this proposition, we can generalize it a little bit. So consider a disjoint union of projective spaces Pi. Here, each Pi is a projective space. This is a disjoint union of finitely many projective spaces. Okay, this index set is finite. So you can think about this as some kind of projective Pn bundle over a finite set. From the proposition, you can prove this corollary. So suppose that you have a permutation. You have a permutation on the K rational point, on the set of K rational point on this disjoint union. And suppose that it satisfies its properties. First, for every I, there exists J such that alpha maps Pi, the rational point on Pi, bijectively to rational point on Pj. Okay. This first condition simply says that it maps points on one of the fiber to another fiber. It won't distribute points to different fibers. It only map things on fiber to things on another fiber. The second condition is I want the map when you restrict on a fiber to another fiber. This is induced by a linear map. Okay, which means that you can write it down in terms of linear polynomials. So under these two conditions, the first condition, it tells you that in particular, alpha induces a permutation on the index set I. Okay, so we have this permutation, and we have the original permutation on the set of K rational points. These two permutations have the same parity. They are both odd or both even. Okay, so why do we need this corollary? This is because this structure, it appears in, for example, when you blow up a number of points on a surface, it also appears in conic bundle. Okay, we need this structure and this result to prove things in these two settings: blow up and conic bundle. Okay, so this is 3A, and yeah, sorry for this undefined notation, but this is the second part in the proof. and which I call it the birational invariance of parity. Okay, this is second part, and then there will be 3B, 3C, and then go to first part. Okay, birational invariance of parity. This theorem says that if you have a bijective birational automorphism over K, and let me emphasize that K has to be F2 to some power greater or equal to 4. If you remove this assumption, it's easy to find counterexamples. Yeah, and finding a pattern in the other over the other field might be interesting. Okay, but anyway, with this ground field given a bijective Cremona, yes, that's this here. Yeah, I forgot to write down something. So I need to start with this ground field and start with X and Y, which are both smooth projective surfaces. Okay. And on this two smooth projective surfaces, you consider alpha, a bijective birational automorphism on X, consider beta, another bijective birational automorphism on Y. And also, I want to assume that there exists a birational map between X and Y. These two surfaces are birational, and H is an example of birational map. And one more assumption, suppose that alpha and beta, they are conjugate to each other under this birational map. Okay, then the action of alpha on the set of rational point on X and the action of beta on the set of rational point on Y. They have the same parity. They're both even or both odd. Okay, so the parity over this ground field, the parity is invariant under conjugation by birational maps. And the key ingredient in the proof of this theorem is a big theorem called strong factorization. The key ingredient is strong factorization. Okay. It says that given a birational map like this, let me write it down here. Given a birational map like, okay, let me write it down here. Over, say everything is over K, where in this theorem, K can be a perfect field. Then you can resolve this birational map by a tower of blowups. So there exists another surface Z, which is obtained by a sequence of blowups from Y, and which is also blowups from X, such that H, such that this diagram commute. So this is a strong factorization. It says that any birational map can be factorized between smooth projective surfaces over a perfect field, can be factorized this way. And using strong factorization, so now in our setting, we have a bijective birational automorphism on X, bijective birational automorphism on Y. With pick one such strong factorization. What you need to do is to prove the theorem, what you need to do is to like blow up more points on each step, such that when you conjugate, for example, beta step by step to z, in each step, you still get a permutation. Because in general, if you blow things up, you conjugate some bilateral homomorphism up, the thing above may not be defined on some new rational points. So you need to control this step by step and also do the same thing. And then eventually you can compare the parity of these two things above and then conclude that they are the same. Okay, but anyway, the key ingredient is the strong factorization. This is the important thing behind this bilateral invariance of parity. Yes. Yeah, and let me return to 3. Okay, so this is bilateral invariance of parity is an application of this corollary. And another application of the corollary occurs when we are dealing with some other maps. Okay. So conic bundles over P1. And say, given conic bundle over P1, and that F to be bijective birational automorphism over K of this guy. Yeah, and moreover, I want this F to, by this group, I want elements here to preserve the fiber class. Preserve the fiber class, which means that you have a map on conic bundle over P1, which maps fiber to fiber. Yeah, so given such kind of thing, I can show that it must induce even permutation. So how do we do that? So given the conic bundle over P1, the fibers has only 4 possibilities. It's either a smooth conic, which is P1. It's either a double line. It's either 2 lines cross with each other. And these 2 lines are Galois conjugate, and they are not defined over the ground field. And the 4th case is you have a degenerate fiber like this one, but with the branches defined over the ground field. Okay, so given a conic bundle over P1, these are the 4 possibilities of the fibers. And if you have a bijective birational automorphism which preserves the fiber class, it will be well defined. So these are the I'm considering fibers over FP, over P1 and over the ground field. Because the map is bijective on rational point, it has to be well defined on all these fibers. And in particular, it will map fibers of the same type to fiber of the same type. So for example, if you consider the fibers of the first type, all fibers are mapped to themselves, and then you can use the corollary to conclude that the permutation above and the permutation below, they have the same parity. And you can do the same thing for a second type of fiber. A double line is nothing but, like in our setting, is nothing but P1. And for this one, this is just a point. Above it's a point, below is a point. So the permutations are totally the same. So permutation above and permutation below, again, have the same parity. This one, you can understand it as this joint union of 2 lines minus a point. Or more precisely, you can consider it as If you union this guy with a point, you get a configuration of point like that. And from there, it's not hard to use the previous cases to conclude that permutation above among this kind of fibers has the same parity as the permutation below. Okay, they still have the same parity. So no matter which types of fibers, the permutation above and permutation below on P1, they have the same parity. And we already know from like the projective space thing, we know that permutation on P1 always has to be even. So permutation for F has to be even. Yeah. And this tells you that fibers like maps like this has to be even. Yes, even.
So far, which of the parity result fails for F2?
Which parity result fails for F2? If I remember correctly, over F2, you can already produce some odd permutation from projective transformation. And also the example I gave in the very beginning, the standard quadratic transformation, it produced odd permutation over F2. Oh, for this one? Which part fail for over F2? I don't remember all the detail, but I feel that I have thought about this, and maybe in each step you can easily find some example. It's easy to, this phenomenon is easy to fail if you are over the other field, like F2. This is the thing. Yes. Okay. Yes. So let me keep going. C for I want to consider Del Pezzo surface, automorphism on Del Pezzo surface. Yes, and I want to say that automorphism on Del Pezzo surfaces also induce only even permutation. But how do we do that? I'll only talk about the case when the degree of the Del Pezzo surface is from 3 to 9. From 3 to 9. And the other two cases are hard, and I don't think I have time to talk about it. And yes, so for a given Del Pezzo surface with this degrees, and 9 in this case, I want to assume my Del Pezzo surface to be rational. And so for so degree 9 is just a P2. Okay, and for Del Pezzo surface, we can produce, we can embed them into P projective space using the anti-canonical bundle by raising the anti-canonical bundle to certain power to produce a projective embedding. Okay, there are 3 things I'm going to talk about in order to give you idea why everything here is even. So the first thing is every automorphism on such kind of Del Pezzo surface over a finite field has to be, the automorphism group itself has to be finite. This is because you can embed X into Pn using this bundle. And if you are given any automorphism, it preserves the projective, it preserves the canonical bundle. So this guy has to induce, so this automorphism has to be induced from some projective transformation of this Pn. So this gives you an embedding of automorphism of X into PGL over K. Here K is any finite field. And because K is a finite field, this is finite group. So this is finite. So this is finite. This is the first thing. A second thing is knowing this is finite, so in particular, given any automorphism, if you want to study its parity, you know it's finite order. You can, for example, raise it to some odd power so that we may assume that the order of f is a power of 2. Because parity is invariant under raising to an odd power, so we can always make this assumption. And this assumption imposes very strong conditions. Like under this assumption, yes, this is the third part. We can use the configuration of -1 curves. This third thing. So under this assumption, and then if you consider the configuration of -1 curve on this Del-Pedal surface, under this assumption, you can always find some curve, some -1 curve, which is either contractible, or if it's not contractible, you can still find some other configuration, some subset from this -1 curve, such that you can do some surgeries, like blow up more thing, contract the other thing, and to conjugate this f to a Del-Pedal surface of higher degree. So for example, if you have a degree 8 Del-Pedal in this setup, we can find some -1 curve, which you can either contract or do something so that you can conjugate your f to a projective transformation on P2, and using bidirectional invariance of parity. And for P2, we know everything is even, and you can conclude that the automorphism induce only even permutation. Yeah, so this is so to prove that this thing is even, we do it case by case by reducing a case with lower degree to case of higher degree. Yeah, this is a very quick and rough introduction about our approach. Okay. Why am I doing that? So yeah. So why am I doing that? This is because of this thing. Yes. First part, decomposition. So first of all, there's a result by Iskovsky. Okay. Which says that if you have a perfect field, and if you consider the Cremona group of birational automorphism of P2 over K, then you can generate it by 24 very explicit type of examples of birational maps, 24 types of maps. Yeah, and the machinery behind this is called the Sarkisov program, if you've heard about this. So we have this result, and then using the same machinery, using Sarkisov program, basically the same thing, we can show that bijective birational automorphism, again over P2 over K over K, a perfect field, is generated by 19 types of examples. And these 19 types of examples of maps, they are subset of these 24 types of maps. Okay, and moreover, each of them, if you're given F, which is one of these types, it's either F is conjugate to either a projective transformation and bijective birational automorphism of a conic bundle over P1 or C, an automorphism of a Del Pezzo surface, a rational Del Pezzo surface. Yes. So yeah, so with this one, with all the previous results, so in the third step, I've already tells you that we can show that this thing, and this thing, they produce even permutation. And moreover, we can write every element here as a composition of this kind of maps, and each of them is conjugate to one of this kind of thing. Together with the directional invariance of parity, this proves that everything here is even. Yes, so this is the rough idea of proof, but as you can see, I have a picture there. So why am I drawing that picture? This is because what I told you is not very precise. For most of 19 types of maps, it's true that F is conjugate to this thing. Okay, let me put one more vocabulary here to make things precise. Most F satisfy this property. But there's one example which doesn't satisfy this property, and it causes a lot of trouble in our research work. So it's called, this example is called quintic transformation. It's called quintic transformation. And in our work, we denote it as F66. Okay. By quintic transformation, I mean this map is produced by the linear system of quintics. Which pass through a point, a fixed point. So you need to fix a point of order 6, point of order of point of degree 6. Yeah. And not only Cannon, but nodal, a nodal quintic. Okay, so you consider linear system, where this linear system, to define this linear system, first you pick a point of degree 6 in P2. Okay, a point of degree 6 is a Galois orbit consisting of 6 points. Each point is not defined over ground field, but the whole thing you can view it as a variety or a scheme, as a scheme over defined over the ground field. But anyway, it's a Galois orbit of degree 6, and then you consider the system of quintics, which are nodal at these 6 points. And this has dimension 2, and you can check that it produces a birational transformation. Okay, so this is how you construct quintic transformation. So this quintic transformation is not in this setting. And in order to deal with this thing, we need to draw this picture. Yeah, so how do we understand this picture? So because time is not enough, I need some help. So can you help me to move this Blackboard to here, so that if there's any people online, they can see it. Okay. Okay, so maybe move it here. Yes, so this is my quintic transformation. And the point of degree 6 is they are base locus of this transformation. So it can be resolved by pouring up 6 points and then contract 6 minus 1 curves to P2. So it can resolve this way. And this blow up will be a Del-Pezzo surface of degree 3. And on this Del-Pezzo of degree 3, you can blow up 2 more points to get some Del-Pezzo surface of degree 1. And from this Del-Pezzo surface of degree 1, there's a configuration of -1 curves on Del-Pezzo surface of degree 1, such that you can use them to, you can contract this configuration in different ways to get this picture. Like here, you contract something to get Del-Pezzo surface of degree 2, and then you contract something to get a quadric. Here by Q, I mean a quadric. Or here, you can contract something to get dp3 and contract more thing to get the p2. Okay, so you can get this picture starting from here by considering all the -1 curve, the configuration of -1 curve here, and contract the curves in different ways. Yes, and in this picture, we know, okay, this is the map we are interested in. And there are some maps which we know how to understand it. This one, and this one. And on this Del-Pezzo surface of degree 1, there's an involution. Let me denote it by beta. There's a famous involution called Bertini involution. Bertini involution. It acts on this diagram, or more precisely, it acts on the set of -1 curves on this dp1 in a non-trivial way. And it maps the set of -1 curves so that the action, so it also acts on this whole diagram, and its action is obtained by like from here to here. It rotates this diagram by 180 degrees. So you can write beta. Yeah, I'll be using a notation a little bit. So when I say beta here, I mean some involution here. Actually can conjugate it down to map on P2, and it maps things this way. So from this picture, you can write beta as F6 composed with like tau1, composed with G, composed with tau2 inverse, and maybe up to some PGL, maybe up to some project transformation. And in our list, we know this guy is even. And we also know that this guy is even. We know how to do that. And from this picture, because this is even, so this has to be even. So this implies that F is also even. Yeah, so we conclude that this quintic transformation induces only even permutation using a slightly more complicated way. And this technique is not invented by us. It has a name called central symmetry. Central symmetry is invented by 2 people I mentioned before, Lamy and Schneider, in their work about proving that plane Cremona group is generated by involutions. Yeah, so I think I've already gone over time, and thank you for your attention.
Yeah, thank you very much for the interesting talk. So are there any questions?
You mean the one you just I think it's also possible to I use strong factorization because remember when I say I need a blow up. So when you blow up, so when you have a bijective automorphism, bijective birational automorphism on X, when you blow things up, you conjugate the thing up, it may not be bijective. And you need to blow up more points to make things bijective. And because the strong factorization involves basically blow ups, yeah, yes, Yeah, you can keep blow up things and eventually compare two things above. It makes argument easier. For weak factorization, I think you need to control not blow up, but also saying something in this direction, and then that direction, this direction. In my mind, this looks like this make argument a little bit harder, but maybe doable, maybe.
Are there more questions? So if there's no more question, then let's thank Guangwen again. Yeah, so next week is a public holiday. So the next seminar will be in 2 weeks by Shou Tanimoto.